This table shows how the quantum numbers can be used to build the orbitals of an atom. Let's invest the time to understand what this table is explaining. N is the principal quantum number. L is the angular momentum quantum number. The sublevel designation is the name of the orbital. M sub L is the magnetic quantum number. The number of answers from the magnetic quantum number gives the number of orbitals present. I've also included a column for the max number of electrons that can fit in the orbitals. Up to 2 electrons can fit in one orbital. The quantum number rules are also included at the bottom of the table. Let's begin with principal quantum number 1. When n equals 1, L can only be 0. The 1-0 combination is given a sublevel designation of 1s. Because the angular momentum is 0, the magnetic quantum number can only be 0. Because there's only one answer for the magnetic quantum number, there's only one orbital present. The one orbital can hold up to 2 electrons. If we look at a table of the atomic orbitals, we'll notice that the lowest energy orbital, principal quantum number 1, only has one orbital, called the 1s orbital. Let's move to principal quantum number 2. When n equals 2, L can be 0 or 1. The 2-0 and 2-1 combinations give us orbitals called the 2s and 2p orbitals. Angular momentum 0 gives us a magnetic quantum number of 0, while angular momentum 1 gives us magnetic quantum numbers of -1, 0, and +1. These answers correspond to 1 orbital for the 2s and 3 orbitals for the 2p. These orbitals can hold up to 2 electrons and 6 electrons, respectively. Back to our diagram, where we see 1 2s orbital and 3 2p orbitals. Let's do principal quantum number 3. When n equals 3, L can be 0, 1, or 2. The 3-0 combination, 3-1 combination, and 3-2 combination gives us orbitals of 3s, 3p, and 3d. The magnetic quantum numbers can be 0 for the 3s, -1, 0, and +1 for the 3p, -2, -1, 0, +1, +2 for the 3d. This corresponds to 1, 3, and 5 orbitals respectively, which can hold 2, 6, and 10 electrons respectively. In our diagram, you'll see 1 3s orbital, 3 3p orbitals, and 5 3d orbitals. For our final example, we'll look at principal quantum number 4. When n equals 4, the angular momentum can be 0, 1, 2, or 3. These combinations give us orbitals of 4s, 4p, 4d, and 4f. The angular momentum gives us magnetic quantum numbers of 0 for the 4s, -1 up to +1 for the 4p, -2 up to +2 for the 4d, and -3 up to +3 for the 4f. The number of magnetic quantum numbers gives us the number of orbitals. In our diagram, you can see 1 4s orbital, 3 4p orbitals, 5 4d orbitals, and 7 4f orbitals. Of course, we can continue with principal quantum number 5, 6, and 7, but we'll stop here. Let's review the table of quantum numbers. N is the principal quantum number, and it tells us the size of the orbitals. L is the angular momentum, and it tells us the shape of the orbitals. Each L has a letter associated with it, and thus the NL combination gives us the name of the orbital. M sub L is the magnetic quantum number, and the results give us the number of orbitals. There is a fourth quantum number, the electron spin quantum number. The electron spin has an interesting history and an interesting math behind it, both of which are beyond the scope of this channel and won't be discussed here. For the first year general chemistry student, however, there are some important takeaways. First, historical evidence shows that the electron behaves as if though it were spinning. It has a magnetic moment which is produced from a spinning charge, at least in classical mechanics. This is why the name electron spin was given. Furthermore, this magnetic moment can have two possible orientations when an electron is placed in a magnetic field. The famous Stern-Gerlach experiment showed that when an electron beam passes through a magnetic field, it is split into exactly two beams. The calculus shows that there are two possible answers for the electron spin quantum number, +1/2 and -1/2. These are the electron spin quantum numbers. We generally refer to these states as spin up and spin down. The electron spin quantum number is denoted by the letter m sub s. The Pauli exclusion principle can be stated in various ways depending on which level of chemistry you are studying. For general chemistry and second-year organic chemistry students, these are two definitions that I have found to be reasonable. First, when two electrons occupy the same atomic orbital, they must have opposite electron spins. And second, no two electrons in an atom can have the same set of four quantum numbers. Recall, there are four quantum numbers: the principal quantum number n, the angular momentum quantum number L, the magnetic quantum number m sub L,
and the electron's spin, m sub s. These definitions, of course, mean the same thing, so let's analyze further. We saw in an earlier video that electrons behave one of two ways, spin up or spin down. You'll see here I have shown a box to represent an atomic orbital and arrows to represent the electrons. There is one arrow shown pointing up and another pointing down to represent spin up and spin down respectively. When drawing electron diagrams, you'll notice when two electrons occupy an atomic orbital, the arrows are opposite spins. Let's look at this from a quantum number perspective now. I'll use helium as an example. Neutral helium in the ground state has 2 protons in the nucleus and 2 electrons. These electrons will occupy helium's 1s orbital. Notice the opposite spins. From a quantum number perspective, these electrons can be assigned a set of quantum numbers. First, they are both occupying the 1s orbital. Recall that 1 is the principal quantum number and s is the letter designation for angular momentum equals 0. Because the angular momentum is 0, the magnetic quantum number equals 0. The significance here for our example is that the 1 magnetic quantum number answer means there is only one atomic orbital, or one 1s orbital. So far, both electrons can be assigned the combination of 1, 0, 0. But the Pauli exclusion principle states that no two electrons can have the same set of 4 quantum numbers. Here, they are different based on their spins. The red electron is spin up, while the blue electron is spin down. The electron spin quantum numbers are +1/2 and -1/2, respectively.